Welcome to FlowRate and the continuity equation. Today I'm going to discuss the discussion map first, then I'm going to discuss with you the objectives of the course, and we are going to start covering the topics that are intended to be covered today. Let me go over the discussion map for the course. First, of course, our topic begins with the study of fluid dynamics, as the title name implied. In fluid dynamics, we're discussing the flow of the fluid through pipes, tubes, orifices, different media, what have you, but our concentration would be more on pipes and tubes. We also touch base on the flow from the tanks due to pressure differences and so on. We would discuss three measures of fluid flow and that are commonly used: Q, W, and M. We're going to discuss those shortly. Of course, we would learn the relationship between different quantities, different parameters, and so on, using the principles of continuity, later on using the Bernoulli equation. But today we are going to pretty much concentrate on the flow rate and principles of continuity, which leads us to continuity equation. So throughout the related lectures, which with some of those that come later, this is the first one, we would talk about Bernoulli equation later on. We would also talk about the different analysis of the energy loss, head loss, and so on. So we would pretty much, our goal would be to analyze the behavior and performance of fluid flow system, whereas up to this point we pretty much concentrated on the static behavior of the fluid. Now we would like to see if the fluid is moving, sometimes at velocities that are causing all kinds of impact on the flow. How would that behave? What would be the behavior of the fluid? So after you're done with this lecture today, you should be able to define flow rate, weight flow rate, and mass flow rate. You would also would learn about steady flow, how to define it, and principles of continuity, relationship between the continuity equation, the volume flow rate, area, the velocity of flow between 2 points in a fluid system. Then later on, in subsequent lecture, we would describe and discuss different types of pipes, tubings, and all the associated topics that come with that. So let me start by discussing the fluid flow rate and the continuity equation. There are three types of, or three quantities that we measure when there is a fluid flowing within a system or in a system per unit time. There are Q, W, and M. Q is the volume flow rate, which is the volume of fluid flowing past a section per unit. Remember that we measure this at a particular section, since the diameter would be different, the pressure would be different. So we need to somehow have a way of measuring the flow, and that's called flow rate. Now we could measure the volume, we could measure the weight, and we could measure the mass. Same fluid at a particular location. So volume, weight, and mass can be measured at a particular cross-section of a system that contains a flowing fluid. How do we measure those? First, let's start with Q. It's the most fundamental form of the three types, Q, M, and W. It's called volume flow rate. It is calculated by simply calculating the velocity of the flow at that particular section and multiply that by the cross-sectional area. That's how we measure the volume flow rate. It's called Q. The units are given here, both in SI units and US customary system units. In SI, the unit for area is cubic meter, and for velocity is meter per second. Multiply the two together, you're going to have a cubic meter per second. And that makes sense because we are actually measuring the volume per second. So that's called volume flow rate Q. What about the weight flow rate W? The weight flow rate W is measured by multiplying the specific weight of the fluid that goes through that cross section by the volume flow rate Q. So after calculating Q, if we multiply that by the specific weight of the fluid, we can simply calculate the weight flow rate. So what we are measuring here is what would be the weight of the fluid and that at that particular cross section at a point in time, for example, in second. As such, the unit for W would be Newton per second. It is derived by simply multiplying the units for specific weight, which is Newton per cubic meter. Multiply that by the unit for the volume flow rate, which is cubic meter per second. That would be Newton per second, the unit for the weight flow rate. Okay. Then let's take a look at the mass flow rate. Now, as you can see, both W, the specific weight, the weight flow rate and the mass flow rate, both are given here. One is the weight flow rate W, the other one is the mass flow rate M, and they are related to the volume flow rate, which is Q. One, in this case, we simply multiply Q by gamma, which is the specific weight of the fluid. In order to calculate the mass flow rate M, we pretty much multiply Q by the density of the fluid, which is rho here, right? So gamma here multiplied by Q would give us weight flow rate, and rho multiplied by Q in this case would give us the mass flow rate as it's shown here. The unit for M would be, of course, we derive that by taking the unit of mu rho multiplied by the unit of Q. So kilogram per cubic meter multiplied by cubic meter by second. That would give us kilogram per second. And that makes sense because we are trying to actually measure the mass. So you see here, it's very important to be able to distinguish between the weight and the mass in general, in engineering in general. But in this particular case, it's even more pronounced, as you can see it here. So the symbols are given down here in this table. The name is given, definition is given, and the units are given. You can see that in both cases you can replace Q with cross-sectional area in which we want to calculate the rate by the velocity of that particular fluid that goes through that cross-section. That would give us the appropriate unit. Both units are given in SI units and US customary system of units. So There are also other ways we can express this. These are three main ones that I just discussed. There are also other units that can be used, and some of you guys may be more familiar with that. Liter per minute in case of dealing with pumps. In many cases, we use liter per minute. And the conversions, or gallon per minute, if we are dealing with the U.S. customer unit and we are trying to measure the volume expressed in gallon instead of liter. As such, the conversion units that are given here in order to convert 1 liter per minute to cubic meter per hour. H stands here for the hour, so this is cubic meter per hour. This is liter per minute, and gallon per minute, and so on. So this is a cubic meter per hour. This is liter per minute. This is also liter per minute, but the conversion would be from a gallon per minute to liter per minute. A conversion from a gallon per minute to a cubic meter per hour is given here, and the conversion unit from 1 cubic feet per second to gallon per minute is also given here. That's within the same system of units, US customer, but we're using different units. So it's important to understand these, have some practice with these, keep them handy on your cheat sheet during an exam. You can refer to it and use these during an exam in which you can easily make the conversions. There are also calculators that could be programmed. You can program them in there. And I know some of you guys also are using computers during the exam. That's perfectly fine to do all of that, as long as you work individually and you have your book and your notes. But instructions during, for each exam would be given in due time, so you don't have to worry about that for now. Okay. So this table provides a typical volume flow rates for different kinds of systems. For example, what is the, if you can see here, the flow rate gallon per minute for an industrial oil hydraulic systems, depending on how what the capacity of the system is, would be between 3 to 30 gallon per minute. And it's also shown in cubic meter per hour. It's also shown in liter per minute. This is a wide range from 10 to 100. It's like 10 times the maximum is 10 times the minimum. So it's really a wide range. Here is like 6 times, from 100 to 600. But it gives you some ideas as to when we're talking about flood control and drainage pumps. If something goes wrong during a disaster, a natural disaster, when people say, well, why can't we just pump all the water out? Here would give us some perspective to us engineers as to we can't take it out because their capacity of the pumps are, they have certain capacities, and we need to bring in more pumps. And it takes time to deploy them. It's the cost that's involved. Problem gets pretty complicated when something goes wrong, because now you have these different organizations that need to interact with one another. So if you're not ready with that's would realize the appreciation of how much appreciation we need to have for cooperation and communication and all that between these different agencies, government, private, nonprofits, and so on, as a result of a natural disaster. So this would also, not directly but indirectly, can show us that, look, if we have this huge volume of water pouring in, of course we need to have, look at this one for mobile equipment, the hydraulic system. The capacity is up to 150 gallon per minute. So if we have this huge inflow of water, of course we need to have many of these, and then you would realize what would be the problems that are involved. Something for you guys to just think about and put things in perspective. So let me start talking about principle of continuity. Principle of continuity works in different aspects of engineering in different ways, although the principles are the same: the conservation of mass and conservation of energy. In this case, we use the same principles of pretty much continuity to derive certain equations that will be used later for our means, fluid mechanics. The principle of continuity, it actually governs the flow of a fluid in a closed pipe system. Okay, that's the principle we use pretty much to drive all the equations that we need. Let's take a look at this particular pipe that's shown down here. The flow is actually upward, not downward, something that most of us we are used to. We're not used to a flow that goes upward. Of course, in this case, it's not going to be a gravity flow. There's a pressure involved, and that pressure is provided by some means, usually the pump. It's going to, pull this water, if you will, up the hill or up this pipe. So there are two sections here, section 1 and section 2, and there would be a fluid flow. Fluid would be flowing past section 1, and it's going to continue, and it's going to pass through section 2. Okay. So the quantity of fluid flowing past any section in a given amount of time is constant. Okay. So it's important to realize that. The method of calculating the velocity of flow of fluid in a closed pipe system depends on the principle of continuity. If you consider the pipe that I just showed you, sections A and B, the fluid is flowing from section 1 to section 2 at a constant rate. That is, the quantity of fluid flowing past any section in a given amount of time is constant. This is referred to as the steady flow, and that's what we would concentrate now. And this is a steady flow. So, of course, we need to realize that from section 1 to 2, we're not going to add any fluid. We're not going to remove any fluid between these two sections. And there is no reservoir in between that we can store the fluid. So these are preliminary assumptions. Otherwise, principle of continuity doesn't apply. So if these principles, these conditions are met, then the mass of fluid flowing past section 2 in a given amount of time must be the same as that flowing past section 1. In other words, we have a point in the system, cross section, point 1, the fluid has certain pressure, and it is passing and continue passing. We're not going to take it out. We're going to have some energy loss, of course, due to the flow itself and due to the condition of the pipes and so on. But principle of continuity governs if we don't add any fluid, store it, or remove it between these two sections. As such, M1, that's the mass flow rate at point 1, is the same as mass flow rate at point 2. Realize what I just mentioned about mass flow rate. M is rho times A times V. That's density by the cross-sectional area or the area of the pipe at this point multiplied by V, which is the velocity at that particular point. So if we have those, then rho 1, A1, V1 equals to rho 2, A2, V2, or rho sub 1, A sub 1, V sub 1, and so on. Very important equation right here. Okay, let's continue. So if you have rho 1, rho sub 1, A sub 1, V sub 1 equal to rho sub 2, A sub 2, V2. This is a mathematical statement of the principle of continuity. This is called continuity equation. This equation that I mentioned here, shown here, also provided to you here, I'm going to write under here. Okay. This is the continuity equation. So every time I ask what would be the continuity equation for fluid flow rate, that would be the continuity equation. If during an exam you ask that question and you pause for a second, that means you're not fully prepared for the exam, because right away, continuity equation, that's the equation for the fluid flow rate, something that you should know by heart when you're done and before you go into to take this exam. So this is used to relate fluid density, flow area, and velocity of flow at two sections of the system in which there is a steady flow. Remember, this is a continuity equation of a steady flow. Okay, not just that. So I need to add that. So this is valid for all fluids, whether they're gas or liquid, as long as the flow is steady. Okay, important to realize that. So we can consider that if we have the incompressible fluid, and of course in this case Q1 would be a Q2, Q is AV, and so rho 1 and rho 2 would drop out because we're talking about a liquid, same liquid. So we're going to cross these two out. Rho 1 and rho 2 is equal. But A1 is not, and V1 is not, and A2 is not, and V2 is not. So A1, V1 would be Q1, and A sub 2, V sub 2 would be Q2. I intentionally use different subscript. Sometimes I call them A sub 1, sometimes I call them A1, so you guys get to know, be familiar with all the terminology, trying to train your ears for those that are watching these lectures. Okay. So from point 1 to 2, the reference point Z, if this is the reference level down here, we pick a level, arbitrary level, as the reference level. Okay. Any point really, in this line, along this line. So the distance from point on the pretty much center line of the pipe right here. If I mark this one, and the difference in head between these 2 points is called Z sub 2. So keep that in mind. We're going to use it later. Okay. So again, it shows here the reference point is an arbitrary level. Okay, here you can continue this. Maybe the pipe ends here, what have you. You can bring this up or down. It really, it's just a reference level. So the distance between this point and that, the vertical distance would be Z1, and the vertical distance between the center point, well, the point on the center line of the pipe of that particular cross section that we're interested in, with the pressure P2, if you mark that at 2, then Z2 would be that distance to the reference level. And you can easily find the between point 1 and 2. If we subtract Z2 or subtract Z1 from Z2, you're going to get the difference in head between point 1 and 2. realize that there's a P1 here, pressure at point 1, and there is a pressure at point 2, not to be confused with rho 1 and rho 2. And here rho sub 1 and rho sub 2, they are equal, so they're the same. So as you can see, we can apply a Q1 equals to Q2, and it's a continuity equation. We can apply it to liquids, and what it really means is that for a steady flow, the volume flow rate is the same as any section. That's what it really implies in plain English language. It can also be used for gases at low velocity. Here, if you go and have high velocities, this doesn't apply. This is, what do we mean by low velocity? Velocity 100 meter per second, less than that. Then we're going to not going to have much error. Higher than that, we're going to have errors. It's not as accurate anymore. It's just an approximation. Let's go over an example. Ignore these numbers for now. It's shown here. At one section in an air distribution system, air at 14.7 psi, and let me give you all the problem. At one section in an air distribution system, air at 14.7 psia and 100 degrees Fahrenheit, that's the temperature, has an average velocity of 1,200 feet per minute, 1,200 foot per minute. Both can be used, and the duct is 12 inches square. That's the area given. Okay? It's 12 inch. Well, we're going to calculate the area. This is going to give you the dimensions, and it is square. The cross-section shape is a square. At another section, the duct is round with a diameter of 18 inch, and the velocity is measured to be 900 foot per minute. Okay, same units, but of course, diameter is also the shape. The cross-sectional shape is different. So in this case, we need to calculate the density of the air in the round section, and the weight flow rate of air in pound per hour. Okay, abbreviated here as pound per hour. So what else do we know? We know that at 14.7 psia and 100 degrees Fahrenheit, the density of the weight. Remember, we have discussed these at the beginning of the course, the density of the air, and you've done problems. You solved problems related to that, so it should not be a stranger to you. Okay, so then the density, which is a variable, as we change it to the temperature and the pressure, of course, that would be different. But the density of air in this case would be 2.2 times 10 to the minus 3 slugs per cubic feet, and the specific weight is 7.09 times 10 to the minus 2 pound per cubic feet. Okay, these are given. Let's solve this problem. Okay. Now, according to the continuity equation for gases, we have, let me go back, rho sub 1, A sub 1, V sub 1 is rho sub 2, A sub 2, V sub 2. We can calculate the area of the two sections since the dimensions are given and solve for rho sub 2. We have A1 and A2, and we also have V sub 1 and V sub 2. That's also given in the problem. If you look at the problem, look back, you'll be able to see that. So, what we do in this case is simply rearrange this equation. It's given up here, and we calculate rho sub 2. We simply rho sub 1, A sub 1, V sub 1 divided by A sub 2, V sub 2. We do some rearranging. We put the similar terms together inside the parentheses, and you're going to have rho sub 1. Or simply we could calculate rho sub 2 over rho sub 1 first and express it in other terms. Then we could have taken rho sub 1 to the right side of the equation and solve for that. A1 is 144 square inches. This is because it's square cross section, and the dimension is given 12 inches. So we simply square that. For a circular pipe, pi d squared divided by 4. In this case, we call that d sub 2, not to be confused with A1 or the dimensions given for the first pipe or the first cross section, square one. So here, pi 18 squared divided by 4, 254 square inch would be the areas. Then, now of course, we're going to calculate the density. We do a substitution here. Previously, we just did this one. Okay, so we have a sub 1, a sub 2 now. We're going to substitute that in the equations that we just developed. The density of the air in the round section is, we can easily calculate that, rho sub 2, using the equations. And we want to make sure that all these units, they cancel out, otherwise we are going to run into problems. This one would cancel with this. Feet per minute is going to cancel with feet per minute. This is all given in the problem. And then from here, rho sub 2 would be 1.66 times 10 to the minus 3 slugs per cubic feet. Okay? So what about part B? The weight flow rate. Now we can find that by using the rho that's given for that particular, by using gamma sub 1 that's given with the conditions that are given at that particular temperature and pressure. In that case, this would be the gamma sub 1 given in the problem. So we don't really have to look that up. It's already given to you. And multiplied by 144 square inch. This is also given in previous step. We already calculated this before we started step A and B. One must be very careful with the unit conversion here. Remember that we want to go to calculate as pound per hour. Okay, so as such, we need to convert anywhere here we see a minute. We need to convert that to hour. That conversion is done here, minute per hour, and this is multiplied here by 60. So eventually, we're going to have actually the h here. Okay, the one that I highlighted in red. We are going to have that h down here, right here, right? And this is the best I can do with an arrow here. So h would show up here, and then we need to make sure that all these unit conversions are met. I'm sure you can do that by now. At this stage of the course, it should be pretty easy for you to do. So W will turn out to be 5,100 pound per hour. Okay. Go through this problem. Make sure you understand every steps. It's really not that complicated, and it's very important for you to understand the basics at this stage. Okay. And if you have questions, of course, as always, use the course website to get a hold of me in case you have any questions or comments. It's the best way to do it. Okay, so I'm sure you find these slides pretty, this discussion and slides pretty useful in your learning. Realize it's going to take me a long time to prepare these slides, so they're just not available. It takes some time to develop them, sometimes many hours. Okay. All right, end of slides. You know what to do if you have any questions or comments. Thank you.